So our topic for discussion today is stress and strain. And this is our very first topic that we're looking at in strength of materials. It basically lays the foundation for some other topics that we're going to handle in future. And as per tradition, we're going to start with the definitions, then later on we'll go to the applications. So to get started, let's look at the key definitions, of course. What is stress? How do you define stress? Stress is basically the force per unit area, or we can use the formula F over A, force over area. You can write this unit, which is Newton per square meter, or you can preferably say Pascal. So instead of this, you can also decide to say using Pascal. That is still the same unit there. Then the counterpart to this is strain. Strain is basically the ratio of the change in dimension to the original dimension. When we talk about the linear strain, then we're talking about this, which is away from the general version. Because we can have linear strain, we can also have volumetric strain, name it. So here we have change in length divided by original length. So we have this symbol, change in length over original. We can also write it in this way, where you've been given the final and the initial length. So you can say final length minus the initial divided by the same initial or original length. So either this or that, either of the two, depending on what data you've been provided with, you can go ahead and calculate your strain or the amount of deformation experienced by a material. So then, how do we put them together? Young's modulus brings together both stress and strain, because Young's modulus, represented by letter E, is the stress per unit strain. Oh, by the way, nothing connected to my name. It's E for Young's modulus, not for Ernest. E equals stress over strain. Again, if you check, the strain didn't have any units, but the units that we were using for stress were newtons per square meter. Stress, the unit is this. Strain, no unit. So we maintain that one. Therefore, you can use that, or you can go the smart way. You can decide to say, let me use the other one, which is in Pascal. You're basically talking about one and the same SI unit. Then Young's modulus basically is the application of Hooke's law. In Hooke's law, we say that stress is supposed to be proportional to the strain on one condition, that you're still within the elastic limit. You may decide to define Hooke's law or to state Hooke's law in terms of the stresses, or you may do that with a force, where we say that this force is supposed to be proportional to the strain, as long as, again, the force proportional to the extension, as long as we are still within the elastic limit. When we exceed the elastic limit, this law does not apply. Now here is our load extension graph for mild steel. Why mild steel? Because different materials produce different graphs, but what comes from mild steel helps us to understand the various factors that we need for this type of analysis when we're dealing with direct stress. So here, I'll label this as point O. You have a material which is being loaded until it is destroyed completely, until it snaps. So this mild steel component was clamped between two ends, then forces were applied. When a force is applied, for example, somebody applies 2 kilonewtons at this point, then they check how much extension they are having. Maybe they have perhaps 0.1 millimeter as the extension, so they record it there, 0.1. Of course, it means it's here, like that. So these will continue like that. In the end, what they will plot as they continue loading you just go ahead and draw a single line connecting all those points that you were drawing. So what you can already notice is that from O to A, it's a purely straight line representing the limit of proportionality. Whereas point B, when you move from A to B, it's no longer that straight. But what is special about O up to B is that all this region here is the elastic region. The material is still elastic. If you stop plotting the material, it will go back to its original dimensions, similar to the way a spring behaves. Apply a force, stop applying that force, it will quickly go back to its initial shape. But point B is our yield point. One thing you'll notice about the yield point is that you can see the trend all where we are coming from here, that the force has been going upwards. But at yield point, you only notice all of a sudden that the force starts reducing from nowhere. That is the process of yielding. So when you reach point C, here we already have now a new shape. So C to D is a permanent set because that shape you have there is deformed. The material you are testing has now been deformed. These dimensions have been tampered with. It's no longer with those you started with. Point D, when you look at our graph, gives us the biggest number of, or the biggest value of your force, representing the force that we can use to calculate the highest stress, the maximum stress, or the ultimate tensile stress for a material loaded in tension. That is the stress at point D. When you continue loading, you will see similar behavior to what we saw here, meaning that your material is now about to snap or break in two. So point E is our break point, meaning the material finally gives in. Those are the same things we mentioned there. Now, what is this UTS? We already said that the UTS for a particular material is supposed to be the maximum stress a material can experience, especially when tested to destruction. In other books, this is known as the tensile strength. So the formula that you can use is just here, maximum load, which is the load we mentioned at point D on that graph we're looking at, divide by the area. Here we are being consistent with original, because as you continue loading the material, as you continue testing this material, the cross-sectional area also changes. So here we are sticking to the original cross-sectional area. So maximum load over original CSA gives us our UTS. The factor of safety. The factor of safety is simply the ratio between the ultimate tensile stress and the working stress. Now, this factor of safety basically is just a number, can preferably between 4 and 8 or 4 and 7. The reason it comes in is to ensure that what we are going to pick as our working stress is safe. It does not allow the material to fail prematurely. It does not allow the material to fail shortly after it is put to use, or even while we're just doing the preliminary test to see if things are working well. And also for it to handle extra loads that it may carry, it may experience along the way. So that's where the factor of safety comes in. So here we are saying our factor of safety, if you're dealing with a material that is loaded in tension, it's UTS over working stress. Now, factor of safety is just a number. It doesn't have units because the units on top and the units below cancel out. It's just a typo error. So that is our UTS. You can make working stress the subject to the formula, and you're going to have it as UTS divided by that factor of safety. The yield stress, basically, this is where now you're trying to calculate which stress can yield the material. So you get the load at yield point, divided by the original cross-section area. What you have now is your yield stress, because that is the stress that can cause yielding. Let's look at some example then. So in this example, we're told we have a component whose length is 50 millimeters. The dimensions are 20 millimeter by 20 millimeter in its cross-section. Then a compressive force of 100 kilonewtons is applied axially, meaning along the axis. And Young's modulus is 2.14 by 10 power 8 kilonewtons per square meter. So what do we need to find? The stress, the strain, and the shortening in length. Stress, strain, as well as the shortening in length of this material, this component. Information provided. The 20 millimeters that you see, you convert each one to meters. This, when you divide by 1,000, you get 0.02, the same with that one. So to get the area, you multiply these two, and that's what you get. And the question could be saying, but how? The shape, we are told that this is the kind of shape we're dealing with. It's basically rectangular in cross-section. It's like this. Oh, please forgive me, that's a straight line. So it's rectangular, then here you have those lengths like that. Again, like that, and then that. And of course, we are coming down. Here it's a, not just rectangular, but basically a square, because what you have below here as how wide your material is, it's 0.02 meters. The thickness of the material is also the same. It's also 0.02. What about the length? The length along here is given as the 50 millimeters. That if I divide 50 by 1,000, I'll get my length as 0.05. So we're saying that my length is actually 0.05 meters. So that's what I'm dealing with. But then this is my cross section. This is the cross section of this material. And to get the area, because this is rectangular, I just multiply this by that. It gives me the cross section, and that's what I have there. Then the length, there we have 0.05. Young's modulus, you can see this is 10 power 8. A kilo is 10 power 3. So 10 raised to power 3 times 10 raised to power 8. I just add the 3 and the 8. Then I have 10 power 11 newtons per square meter. Newtons per square meter, or basically Pascal. Newtons per square meter, it's the same thing. So we convert this to the normal unit because we cannot leave it like that. The force is compressive. This force is basically compressing the material, reducing its dimensions, squeezing it apart together. So because it's compressive, that's why it's supposed to carry a negative. If it was a tensile force, a pulling force, a force that is basically trying to pull the material apart, increasing its dimensions, this was supposed to be positive. So we're just going to write 100,000. But because it's a compressive force, that's why we have negative 100. And it's a kilo newtons. So it's 100,000 newtons. Part A, we're looking for the stress. Stress is force over area. The force was negative 100,000 divided by the area, which is 0.0004. How many zeros? 3? 0.0004. You enter that in your calculator, your answer comes out as negative 2.5 times 10 power 8 Pascal, or times 10 power 8 newtons per square meter. That is your stress. Then strain, which is the next part we're looking for. we realize that we do not have the change in length and the original length, or name it. What we simply have is Young's modulus. So we review this relationship here. According to this relationship, we realize that when you define Young's modulus, it's stress per unit strain, stress over strain, the ratio between the stress and the strain. That is Young's modulus. So try to make strain the subject of the formula. This is what you have. It will then be stress over Young's modulus. So then you can just do the substitution. Your strain is negative 2.5 by 10 power 8 over 2.14 by 10 raised to power 11. Then our answer is negative 0.001168. What about the shortening in length? Basically, we're just talking about the change in length. We can now go back. In fact, this is our C. That is our part C. Looks a bit funny. Let me just remove first. So what about the shortening in length? We're saying this is basically our part C. We review the formula for strain, which is defined as change in length over original length. So what we're looking for is this one on top, which is the change in length. Make it the subject simply means we're cross multiplying. And we have the change in length being equal to original length multiplied by strain. So you multiply 0.05 multiplied by negative 0.001168. Then your answer is negative 5.85 times 10 power negative 5. That is our shortening in length. That is, and please just leave the answer here. This is the interpretation of that answer, and we've left out the negative because we've already said shortening. What if you're dealing with a hollow material, a material with a hole inside, meaning that it's not a solid material like the one we have? Here we have it. So this one now is a hollow shaft, meaning that the material is simply there. And this drawing comes from the information that has been provided. Look at the way the information has been given. What we have is that the length is 4 meters. This is a hollow cast iron cylinder length, 4 meters. The outer diameter is 0.3. Then we also have a thickness 50. So this is the thickness, meaning from here to there, you have it as our 50. The thickness, meaning the same thing. It's the same thing you have there. This is also your thickness. Now, the internal diameter, this one hasn't been given, which is our D here. So if you're looking for this D, we're basically saying that small letter d is supposed to be equal to, if I call the outer diameter as D1, it will mean I'll say D1 minus twice the thickness. So if I want now, I can simply do this. I'll say this is equal to, the D1 is the one we have as 0.03, then minus, I'll just use the brackets, and I said 2 multiplied by the thickness, which is 50 millimeters. If you convert 50 millimeters to meters, it becomes 0.05, 0.05. So what we are having with this combination is just, let me just write it here. It is our not 0.03 here, please. It's just 0.3. It's not 30, but 0.3. So I'll just remove this. 0.3. Now, 0.3, the one I have there, 0.3 minus, if I multiply 2 by 0.05, I get 0.1. 0.1. So this is the 0.2 you see here as our internal diameter. Okay, so we need to find the force, the strain, the total increase in length, and the final length of the cylinder, including the percentage elongation. So with the information provided, first of all, we've already established that the length is 4 meters. The area is pi d squared over 4, but this is a hollow shaft. It has this hole at the center. Material has been removed from here. So we say pi d1 squared minus pi d2 squared. Factorizing such an expression leads us here. Pi d1 squared minus pi d2 squared is the same as pi d1 squared over 4 minus pi d2 squared over 4 is the same as factorizing it where you have pi over 4 d1 squared minus d2 squared. Then let's do the substitution. So here now I have 0.3 squared minus 0.2 squared, giving me this value for the area. Then stress, it says 75 kilonewtons per square meter. So it's 75 million. The other one, again, it's kilo here. So if I say 10 power 3, then times 10 power 8, it becomes 10 power 11. So I start with the first one. I'm looking for the force. Since I already have the stress, I can make force the subject. I'll simply say force equals stress multiplied by the area. Basically, I'm just cross-multiplying. So 0.03927 times 75 million. Then that's my answer, 2.945 meganewtons. Strain. Already we had established that when you don't have those changing dimensions and the others, you can review the formula for Young's modulus. So you make strain the subject, which is now stress over Young's modulus. So then your strain becomes 75 million over 1.6 times 10 power 11. Here, I think I'll just make a correction. It's supposed to be 1.56, but we'll correct it and synchronize it with what is in the question. So 1.6 by 10 power 11. When you divide those, what you get now is that 0.00046875. Now, what about that change in length we talked about, the increase in length? So again, you make change in length the subject, multiply the original length by the strain that we just found. So our original length is 4, the strain is 0.30 and then 46875. So we have our change in length being equal to 0.001875. What about the final length? The final length simply means that you have to add that increment to the original. Add the increase to what you started with. So change in length plus the original length gives us that final. So this plus that, 4 plus 0.001875, giving us 4.001875. The last one is now the percentage elongation. In the percentage elongation, we're saying it's basically just supposed to be change in length divided by original length, express that as a percentage. Let me go through that again. Percentage elongation is the ratio between the change in length to the original length expressed as a percentage, meaning that you multiply that now by 100. Now look at what we've written here. This is change in length over original length. It's just the same thing written there. We are simply saying this is the same as strain. So meaning that if you already have strain, you can just say strain times 100 is the same as what we've written here. So moving on, You can pick the strain we just calculated, which is that the strain we had was this one. So 0.000046875 times 100, giving us 0.046875%. So that is our first part in strength of materials, referring to direct stress. Again, I have an exercise for you after this, which you can feel free to go through and let me know how things are moving. You can post a comment or reach out.